Okay, let's get started today. So last time we basically introduced the course and introduced some basic knowledge of algorithm design. So the main focus today is I'm going to introduce graphs. So one notice that I would like to mention is that later today, I think basically by tonight, we will post assignment 1 into our course website. And the deadline is going to be 2 weeks from now. So basically before lecture 4. So today is lecture 2. And the deadline of assignment 1 is going to do like 3 p.m. September 27th, which is basically the lecture 4 time. So we will definitely also make an announcement at the course.pku.edu.cn, but just I would like to notice that there is going to be a homework assignment tonight. Okay, so let's get started and talk about graphs. So last time we basically talked about some basic definitions, and I think towards the end of the class we talk about a few basic definitions. So we talk about paths. So path is basically an undirected graph. So if you want to consider path in an indirect graph, that is basically a sequence of nodes v1, v2 until vk, such that basically for any one for any I between 1 to k minus 1, then basically you have an edge between vi and vi plus 1. And also we call path as simple if all the nodes are distinct. So following the definition of path is very natural to consider definition of connectivity. So basically we want to understand whether the vertices are connected. And basically in an undirected graph, it is connected if for every pairs of nodes u and v, there is such a path between u and v. And subsequently, we can have definition of cycles. And also basically cycle is the case that it is that there is an edge between the last node and the first node. And correspondingly, we can define a definition of trees. So trees are basically undirected graph, which is connected and does not contain a cycle. And follow that, we have the definition of a rooted tree. So rooted tree is basically a tree where, for instance, maybe you can regard one of the nodes as the root, and then you see from this as a root, and you just going down like this. So basically, as we mentioned, for instance, this example. So for this example, you can clearly see that this is a tree. But maybe, for instance, on the other hand, you can consider this as a rooted tree, maybe rooted at r equals to 1. Then basically, we can rearrange the graph like this. So this is basically the definition of rooted tree. And in our course, we will see several times of how rooted tree, is a good form to formulate some algorithms. Today, we are basically going to continue the discussion. Maybe let's talk more about some characterization of the trees as a start. So let's maybe first give some theorem, because for instance, when I just mentioned here, tree is an undirected graph, which is connected but does not contain a cycle. This is still a bit abstract, and maybe we want to have a better characterization for this. So let's write a theorem for this, and maybe let's discuss a little bit more about how we want to characterize a tree. Theorem. So basically, we let G be an undirected graph. On n nodes. So I think I'm trying to actually write a bit larger so that you can maybe see my writing more clearly. So basically, we say that any two of the following statements imply the third. So what are those? First, G is connected. So second, G does not contain a cycle. Third, G has n-1 edges. So any two of the following statements imply the third. So basically, the first and second, if we put the first and second conditions together, that's basically the definition of the trees. But I think a sharp discussion here is that basically we can see that G basically has n-1 edges. So maybe, for instance, let's take a look at this graph as an example. So by the indexing of the nodes, it is clearly seen that basically this graph has 9 vertices. So what is the number of edges? I guess it is not very difficult to check that this graph has actually 8 edges. So this is basically some thought, and actually think about how you would like to draw a tree here. I mean, if you just like draw something like this, then I think basically, intuitively you can see that why basically a graph, if it is connected, I mean, it does not have like a vertex like this. You don't have like a 10th vertex like this. But basically, as long as you draw the graph and you want to make sure it is connected and does not have a cycle, it seems that basically probably the number of edges should be a -1 intuitively. And I think for this discussion here in the class, I'm going to prove this rigorously. So our proof is going to be based on induction on n. So in general, when we talk about graphs, I mean, n equals to 1, I mean, if it's just like a node, or maybe like n equals to 2, but this is probably just trivial. And maybe let's just, for instance, like say n equals to 3. So let's consider like a graph n equals to 3, and we consider like all these conditions. And actually, it is not hard to see that any two of the conditions give this graph. So basically something like this. So why is this the case? So if you want to consider a graph which has 3 vertices and also the graph is connected, then it either looks like this or it looks like this. I mean, I'm talking about, as always, I'm talking about simple graph. I mean, you can have a lot of edges between vertices, but here I'm talking about a simple graph where we don't have self-loops and at most the number of edges between 2 vertices is at most 1. So basically it is either this or this, but for either of the condition, you can see that basically this is not the case we want to study. And basically any two of the conditions will give you this. So basically we are good with the start of the induction. So next, so we assume the correctness at n-1. So basically, if you want to show the correctness of the theorem, we basically need to show 3 things. So basically, we need to show that 1 plus 2 implies 3, and 1 plus 3 implies 2, and also 2 plus 3 plus 1. So we will actually maybe for the convenience of our discussion, maybe let's first assume the case assume is true. So assume 3 is true, then we know that there exists a vertex such that its degree equals to 1. So why is this the case? So recall the fact that the 2 times the number of edges equals to the summation of the degree of all the vertices. And basically by the assumption of 3 here, so G has n-1 edges. So this equals to 2n-2. So all the terms in this summation, they are non-negative integers, and they are actually n terms, because the number of vertices is n. So this just like we can have this fact by the pigeonhole principle. Such an U exists. Otherwise, if all the vertices has degree at least 2, then the summation should be at least 2n, which cannot take it, the summation cannot be 2n-2. So I guess this is something relatively easier to observe. Then maybe let's make more about the discussion here. So maybe let's first consider a case where we have 3 and 1, and we want to imply 2 here. So 3 and 1 is just like G has n-, and also on the other hand, the graph is connected. Okay, so basically, the argument is that why we want to specifically look at a vertex where the degree, a corresponding degree is 1. So let's maybe just, for instance, let's draw the graph like this. So this is U, and because we know that has degree 1, then basically there exists exactly 1 edge like this. And basically, maybe you have the other parts of the graph where we can call it G prime. And this in total is your graph G. So, oh, by the way, one thing we want to mention is that we cannot have a vertex whose degree is zero here. I mean, if we have the assumption one here, then basically and actually for all of the discussions here, as long as we talk about connected graphs, it does not make sense to consider like vertex whose degree is zero. It's just like does not work here. So that is why we actually mentioned that the degree of U here should be 1. So continue with the discussion here. So, and maybe let's assume like both 3 and 1 is true. Then basically, let's say like after removing U here, then basically we consider this a graph G prime. So the graph G prime actually has V, maybe we call it like a V prime, which is like a V by taking out the vertex U here, and also like a E prime, which is the edge set. But we actually take out a specific edge UV here. Maybe let's for this, there should be a V here. So we think about what G is. Oh, sorry, what G prime is. So basically G prime is connected. So this is just by the discussion that original graph G is connected, and also U only has one edge to the part of G prime. And if you remove this edge, you can see that actually G prime should be a connected graph. So G prime is connected and has n-2 edges. So this is just due to the fact that when we consider E prime here, we actually exactly delete one edge from the graph. And if we know originally the graph has n-1 edges, then currently the G prime has n-2 edges. So this you can clearly see just by induction on n-1, then basically G prime does not have cycles. And as G prime does not have any cycles, and there's like a single edge from U to G prime, then this just implies that G does not have cycles. And therefore, we just make the argument that 3 + 1 is going to imply 2 here. Any questions? Okay. So I guess this argument is relatively clear, and as also see the other one that is actually 3 + 2 + 1 here. So let's still look at the graph here, which is basically still this one, which is actually still this one. So the argument is basically the same, that we can let's just write everything down for the rigorous of the proof. So after removing U, G prime, or is still we use this notation. Sorry. But the argument is actually slightly different. So here we argue that actually G prime actually does not contain cycles. So recall that when we want to have like 3 + 2 imply 1, that basically we have the assumption that the current graph has n-1 edges, and actually the current graph does not contain a cycle. Recall that if we want to delete a certain edge, for instance, here we are deleting the edge between U and V. Deleting edges will never increase the number of cycles. I mean, delete an edge does not create any cycle. So as long as your original graph G here does not have any cycle, then G prime should not have any cycle. So G prime does not contain cycle, and also on the other hand, G prime has n-2 edges. So this is also similar to the argument here that we delete exactly one edge from a graph whose number of edges is actually n-1. No, we still assume a 3. So G has n-1 edges, and this is still correct. Or maybe let's just say like this. I mean, such that. Oh. Yes. Otherwise, this is not true. I mean, I'm talking about like a simple graph here. I mean, we don't talk about a case where we have like an isolated vertex, like multiple edges and self loops, etc. Yes. I mean, yeah. But thanks for asking. I guess if you want to say everything very rigorously, we just in general just consider the graph where the number of like each vertex has degree at least one. Yes. Maybe for the beauty of the
I have a question.
writing here is. So here, let's continue with the discussion that 3 plus 2 imply 1 here. So basically, the G prime here does not contain cycles, and also G prime has a -2 edges. So basically, we can then use the assumption from the induction that basically G prime is connected. But here, you're actually adding another edge. So basically, this part of G prime is connected. So if you look at this part, and also you have another edge here. So basically U is also connected to the other part of the graph. So this just implies that G is so basically this finished the discussion that 3 plus 2 imply 1. So the only remaining thing is that we want to be careful and we want to have like 1 and 2 imply 3 here. So still, we want to first prove that there exists a U such that its degree goes to 1. But keep in mind that here the assumptions that we have are that G is connected and also G does not contain a cycle. So we don't have like an argument on the number of edges here. So at least this argument, we cannot directly use this argument. But we are actually going to use the graph property that basically this connected property and also the acyclic does not contain a cycle of this kind of property to imply that there must exist such kind of U here. So how does this work? So assume the contrary, that the degree of U is larger than 2 for any U in the vertex set. So there are basically 2 edges actually for each of the vertex. So basically, we look at the 2 edges. For instance, you start at a U1. Then basically, it has 2 edges. I mean, we just choose one of them and it goes to U2 here. And U2, because the degree of U2 is actually larger, at least 2 here. So there is only 1 edge. You should be able to find the other, which is U3. You have U4, etc. But you don't have infinite number of vertices here. So finally, there should exist an M. So basically, this M should be at most, let's say, n plus 1, such that basically UM coincides with an earlier UI. So basically, you go from U4, U5, etc. But finally, maybe let's say you go back to U2. So this basically can happen. Maybe basically this. Let me see. This is basically there's like U minus 2 and U minus 1, and basically here this U2 equals to UM. Because this graph is not an infinite graph. Ultimately, if all the vertex have degree at least 2, you will actually get such kind of collision that basically UM equals to U2. But this actually gives a cycle. Contradiction. So basically, this is still correct that there actually exists a U such that the degree of U is exactly. So then we are actually good. We just like basically look at this again. So we have U, and basically we have this G here. And sorry, this subpart is G prime, and as the notation above, this whole part is G. So basically, we still, as we mentioned above, so we consider this G prime. where this v equals to like we take this u out, and basically for the edge set v equals to take out this. So basically, this G prime is actually connected, still connected, and actually the E prime maybe sorry, and also the G prime is acyclic. So by acyclic, it just basically does not contain a cycle. And this basically implies that G prime has n minus 2 edges by our induction, and actually we can have that G has n minus 1 edges. So this basically finished our discussion that in general, if you want to look at a tree and we have the assumption that all the vertex has a degree at least 1, then basically the graph, if the graph is connected, it is a tree. It suggests that this graph is connected and does not contain a cycle, and basically the graph has the -1 edges. And basically in our theorem here, we prove actually a quite strong result that any of the two conditions here is going to imply the third. So is this proof in general about like characterization of trees clear to you? Is there any question?
Hello, can you hear me?
Okay, so if this sounds good to you, let's continue with more like advanced problems and settings that maybe we want to actually study in this class. So we now consider a problem called the ST connectivity problem. Yes. So basically, we are given two nodes. And the question is that, is there a path between S and T? A path. So there's question from audio professor. Let me see. Or maybe let me actually open the black box here. Oh, the TA. So one of the student is left in the Tencent Zoom meeting. Maybe you can let the student in. So David, maybe you can say your question maybe in audio. Or maybe
someone else use the audio to he has a question. I don't have a question. Yeah.
Okay.
Yeah. But I forget the name of the guy who like use audio to ask a question. Yeah.
Okay. So maybe the student can ask a question now. Or maybe
I turned on the mic a while before to ask you if you could let Benjamin into the meeting. That was it.
Oh, okay. So Benjamin, are you currently in the Zoom? Sorry, in the Tencent meeting?
Yes, I'm here now. Sorry, my computer disconnected before.
Oh, okay, got it. Okay. Yeah, so I think maybe just for the convenience, I'm opening the chat box here. So I guess for offline students, can you still see the writing? I'm trying to hopefully I'm actually trying to read the things larger. I mean to make everything clear. Okay, so we finished the discussion of the tree and actually the characterization of trees, and now I think we are actually moving to some more advanced problems. So this is the definition of ST connectivity problem, and I think this is just like a study like the connectivity, like whether there exists a path like between them. Maybe we want to actually make a better characterization of this, and of course you can imagine that there can be a problem called ST shortest path problem. So for the shortest path problem, it's just that that given two nodes S and T, what's the length, the shortest path between S and T. So I guess in general, you can see the intuition that basically such kind of connectivity problem and also the shortest path problem, they can probably be of general interest and potentially has many applications. So maybe let's just write down a few. So for instance, maybe we want to consider a problem like a maze, a traversal. And in general, if you have a maze here, you really want to find like a relatively short path that you can actually travel through from the entrance to the exit. And maybe also like, for instance, maybe in network science, maybe you want to have like a fewest like number of hops in a network. Etc. So such kind of like a shortest path problem is in general of a lot of interest and you have a lot of applications in many practical situations. So let's think about how actually we are going to introduce, how actually we can give a good algorithm for finding like a shortest path. So intuitively, this is some sort of like a search problem that you want to like, for instance, if you want to start at a point S here, you want to search, maybe in some sense you want to like find a position of the T here that basically hopefully this is does not take you too much time and also on the other hand can give you a shortest path. So speaking of this search, I think we basically want to make everything more rigorous and actually how we are going to give a good algorithm that can find this T in a relatively short time. So by this search, I think basically in this class, I'm going to introduce two kinds of ways that maybe in general, we want to study this connectivity problem and also like a shortest path problem. So the first kind of search idea that we are going to introduce today is called the breadth first search. And for abbreviation, we just write BFS in this class. So what is a BFS? So intuitively, it just we just explore outward from S in all possible directions. Sorry. So this all possible direction is just the meaning of like a breadth for search. And actually we are making the breadth to be our first priority. And actually we are going to add in nodes one layer, sorry, at a time. So what do I mean by that? That basically means that our algorithm going to look like this. So for convenience, we just call layer 0 to be only the vertex S here. The first layer is going to be all neighbors of L0, which is just all the neighbors of the vertex S. And L2, I guess correspondingly, you can imagine that we want to consider all neighbors of L1. But basically, we don't want to make something confused. For instance, you have like an S, and maybe let's just say that this is like a V1, and this is basically like a V2 here. Or maybe let me actually draw this larger. So assume that maybe you have an S here, and you have like a V1, and you have a V2 here. So for instance, if your V1 is connected to V2, then basically, if we just like use this definition, we are going to get confused. When you actually read down L1 here. So basically both V1 and V2, they're actually in L1 here. But if you look at L2 here, then basically they are still in L2 here because V2 is the Weber of V1. And actually, if you just like, for instance, look at this path. This path has length 2, and this basically suggests why V2 is actually should belongs to L2 here. But if you actually continue with such kind of definition, you will actually just get confused because we want to talk about like the shortest path. For instance, of course, in this graph, you can easily see that the shortest path from S to V1 and also S to V2. I think this shortest path, they are both, the length are both 1. So basically, you just consider these 2 edges correspondingly for V1, V2 respectively. So this definition is probably not the best. And actually, we are going to do something a little bit more clever than this. And actually, this is not so difficult. That in general, we can just consider like all nodes that do not belong to L0 or L1, and that have an edge to a node in L. I guess this makes everything actually in a clearer position, because basically we each time when we want to consider the next layer, we just exclude the nodes from previous layer, and then we consider all the nodes that has an edge actually to the layer that we want. I mean, that basically means, for instance, we want to consider the layer like I plus 1, then basically that is all nodes that do not belong to L0 union L1, Li, and that have an edge to Li. So is this clear to you? Okay, so I guess this is relatively simpler to understand. I'll give a theorem along this. So a theorem. So for each I, Li consists of all nodes at distance exactly I. From S. And this is basically give you an answer to the shortest path problem. And in general, let's also think about the connectivity problem. So the ST connectivity problem. So basically such kind of construction also gives you an answer. So there is a path from S to T if and only if T appears in some layer. So maybe let's actually take a specific look and maybe talk about some examples. Maybe let's, for instance, consider this graph. So I think this graph appears in maybe in the lecture last time, but actually let's right here. So maybe like a 7 and like an 8 here. We have a 4, 5, 6. So let's think about this this graph, and maybe for instance the S here we studied is S equals to 1. So what is like this? The layer of this graph is going to look like. So we have a 1 here because we are talking about S equals to 1 here, and this is going to be layer 0. So what is going to be the vertices in a layer first? Yes, exactly. It is going to be 2 and 3 here. Well, guess the drawing here is not so good. Let me actually 2, and this is going to be 3. So how about layer 2, the second layer? So here, let's just maybe, for instance, first look at 2 here. So the neighbors of 2 here are like 1, 3, 4, 5. But actually, the 1 and 3 here, they already appeared earlier, so that is not where we are actually interested. So we are actually going to have like a 4 here, and also a 5 here. So how about like if we want to look from the vertex 3 here? So then basically we have a 7 here and an 8 here. And I think this is not finished because we want to continue to look like of 8 here. But actually we are good with 7 and 8 here because like the neighbors of 7 are 3 and 8, and the neighbors of 8 are 3 and 7. So these already appeared earlier. So this is basically what we have been written down here. So that is not a problem. So the only other thing that we need to actually take care of is the vertex 5 here, and actually we have a 6. So in general, you'll see that this graph, I mean, this actually defines a tree here. So this tree is actually simpler than the original graph, and maybe let's use some red color here. So you see, actually, there exists an edge between 2 and 3 here, and also there exists an edge between 4 and 5, and also an edge between 7 and 8. So basically, we use this red color to represent edges of G that does not belong to the tree. But in any case, I think this basically, if you want to consider ST connectivity problem, I guess basically this structure is giving you a clear sense about what is the distance from the shortest distance from S to the corresponding vertex here. So I think we are basically going to give a better understanding about like this kind of tree, and maybe let's first discuss about like a property that we are going to use in the discussion. A property. So basically, sorry. So I think I should probably mention, but basically this this tree T here is called like a, because we are talking about breadth first search, and actually by breadth, and I guess you can clearly see the intuition that at each of the vertex here, we basically try all of the neighbors here, and we do this again and again. So basically, in general, this is called like a BFS tree. So the property is that we consider a tree, a T be a BFS tree. Equals to E, and we let, maybe we just consider an arbitrary edge, E and edge. Then the level of X and Y differ by at most 1. So I would like to mention that here, there is actually some ambiguity here, because I'm talking about like TB, a BFS tree, but BFS tree of who? So here you can imagine that you have a certain graph here. I mean, if you look at the BFS tree looking at the vertex 1, or if you look at vertex 2, they're definitely going to give you a different BFS tree. But actually this property, I mean, in general, the argument is that for an arbitrary BFS tree for the graph, I mean, you just look at starting from like an arbitrary vertex, this property is actually going to hold. And I guess this is relatively easy to show, because this is just like a one-line proof. So if that's not the case, sorry, that's not the case, it means if this is not true, I mean, then basically the level of X and Y differ by at least 2, then a contradiction happens. When you move from the small layer to the large layer. Small layer. So maybe let's just, for instance, let's maybe say that X belongs to Li. So from a small layer to because it means that actually they differ by at least 2, but you after all should have the case that Y maybe belongs to L, maybe I plus 1, or maybe union by Li. I mean, if the depth of Y here is larger, at least as the same as X, it can only be the case that this Y here is at the same layer. I mean, also at Li or at Li plus 1, because after all, you have the edge. After all, you have the edge. I mean, XY belongs to E here, and you should be able to reach Y actually at most at Li plus 1. So basically, this finished the discussion of the property. Okay, so I guess you can see the correctness that basically this kind of BFS tree is going to give you a shortest path from S to T. But I mean, we actually in this graduate course, we really want to have a good understanding about what is the time cost. I mean, in general, what is the complexity of constructing such a BFS tree? So this is something we want to be a little bit more careful next, and actually let's discuss about the running time of the algorithm. So by actually the algorithm, I mean, in general, if you consider such kind of things, I mean, you consider such kind of layer construction. And maybe you can see that you're actually going to try because the layer here, I mean, it has a relatively complicated structure, and maybe you want to think about a more like an intricate data structure to actually, in some kind of sense, to give a good maintenance about like the layers. So this is basically some algorithm we want to pay attention to, and maybe let me just write down the algorithm. So this algorithm is just called the algorithm of BFS. So as I just mentioned, in general, it does not directly make sense to talk about BFS. You need to specify like a starting point. So let's talk about the BFS at the point at the node S here. So we do something like this. So basically, we keep a data structure we called a discovered. So basically, we initialize discovered. So basically, we initialize the entry S to be true and discovered V to be false for all other V here. And as basically as we discussed about, we are actually going to have like a 0th layer. So basically we're going to initialize like L0 is actually just going to be the vertex S. And we are going to have like a layer counter I equals to 0. And also currently we don't have anything yet. So we just call the BFS tree to be the empty set. So for student not familiar, this is just the empty set notation. Okay, so we consider an iterative algorithm that while Y is not empty. So for instance, I mean, this L0 is of course not empty because we have just started. I mean, if at a certain point you cannot further add any vertex, I mean, that basically means we just basically figure out the kinetic component, and that is supposedly is at a time that you should probably stop. But as long as maybe at the current level set, there are still a new discovered vertices, I guess you can imagine that we should not stop. And that is the reason why we actually set such kind of like a while loop here. So while LI is not empty, and actually we are going to figure out the next level side. So of course, we are actually going to initialize an empty set. Sorry, an empty list L plus 1. And the next thing that we are going to do is that we are actually, because we need to create what is the next level. So basically we just try all the current nodes in the L1 here. So we just like for each node who belongs to Li. Maybe let me actually use a red color here to make everything clear. So we just consider is there each edge UV belongs to the edge set. So this actually becomes a place where this discovered makes sense, because this discovered is actually basically going to help you in the sense that we basically, as we discussed just now, we want to make sure that these conditions, they actually work, that we don't want to add nodes that are previously added in earlier layers. So this is going to make everything messy, and this is not the case we want. So basically we have kind of like an array here of discovered here is just like going to make sure that this is everything is actually taking a good control. So basically, if we want to now consider like each newly added edge, I mean UV belongs to E, then basically we consider like this. So if discovered V is false, meaning that it has not been discovered before, then we set it to be true. And of course, after setting it to be true, we are going to add edge UV to the tree. And of course, we are also going to add V to the list. Oh, I lost one. So this is basically something we actually work in the algorithm. And I think for the while loop, because we need to each time we want to consider the next layer. So the very last sentence of the while loop is that we want to increment the layer counter by 1. The layer counter I. So this is basically the BFS algorithm. So do you find this clear? Any questions? Okay. So let's prove something, and actually let's give more analysis about the BFS algorithm here. A theorem that we can show is that the BFS algorithm of runs in this time, OM plus N time. So let's just recall that we typically use M to represent the number of edges, and N here the number of nodes, also called vertices. So the BFS algorithm runs in time O M plus N. So if the graph is given by the adjacency list representation, this is basically recall the adjacency list representation that we actually introduced last time. So I think basically for this for this lecture until 4 p.m. I guess we are probably not going to have time. I mean, we only have 3 minutes until a break. So maybe let's leave the proof to the next hour. But I think one thing that we want to actually maybe let's just very early give a remark here. So some student may have the question, I read like OM plus N here. Maybe some students is going to ask like, why not O of M? So because typically, I mean, we in general have M is larger than N, so this looks a little bit weird. So the thing is that actually, I mean, for the lecture, I mean, we assume, I mean, the degree of U here is larger than 1 for all of the vertex here. But actually, I mean, this can be realized. I mean, in general, it is okay that you consider like some isolated vertex that does not contain any edge, and it still makes sense to consider BFS. But for instance, maybe you have like a 9 at a 10 here, then the BFS cannot find it. Maybe like 9 at 10 here. But in general, you just consider like the algorithm BFS here. It seems that you, at least when you initialize an array here, the discovered array here, you are actually going to have the cost. I mean, if you have like a million, maybe this is like a graph only having like 8 vertex, but there is a million vertices that is not connected to any of the other, but it is still in this graph, then you're actually going to pay this cost. So basically, it's just like for our convenience. I mean, for our convenience in the class, we in general assume that there is no isolated vertex. But just like think about everything rigorously. I mean, in general, writing this as like OM plus N does not, at least make things clear and fixes this. And I think this is also typically the case when you see like the graph has a complexity OM plus N, and typically for safety reasons, you can just write this as OM plus N to make sure that everything is well covered. Okay, so this is basically this algorithm. Maybe let's continue in 10 minutes.